In this lecture, we're going to talk about related rates problems. And these are problems where there are two quantities that are related by some equation, and where as one of them changes over time, so does the other one. So in general, you might have something like y is a function of x. So then if x changes over time, well then of course y changes over time. You can think of x and y as both being functions of time. And since they're both functions of time, that means we can talk about how quickly they are changing, which is to say their derivatives with respect to time. And it turns out that in this case, the derivative of y with respect to time is equal to the derivative of y with respect to x times the derivative of x with respect to time. And in fact, this is just another way of writing the chain rule. Also, let me point out that there's no magic in the letters x and y. So you could have something where, say, w is a function of p, and maybe p and w are both changing over time. And in that case, the rate of change of w with respect to time would be the rate of change of w with respect to p times the rate of change of p with respect to time. Notice it even looks kind of like these dp's should cancel. That's not really what happens, because dw dp is just a piece of notation, and so is dp dt. They're not really fractions. But nevertheless, the fact that it looks like they cancel can kind of help you remember how to build one of these problems. Okay, so that's the basic idea behind a related rates problem. Let me look at sort of a typical example. So let's suppose that, say, a circle is growing over time. Maybe the radius is increasing by 2 centimeters per second. And we'll ask, how quickly is the area changing when the radius is 5 centimeters? Okay, so how do we deal with a problem like this? Well, first of all, let's try to kind of chew through and digest the word problem and just turn it into a mathematics problem. Right, we have a circle that's growing over time, and we're asking questions about its radius and its area. So it stands to reason we will need the formula for the area of a circle, that the area is given by pi r squared. Now, let's go through the remaining sentences. We said that the radius is increasing by 2 centimeters per second. Now look at the units on that. Centimeters per second. That's units of length divided by time. And that is a little bit of a hint that this is talking about dr dt. Right? It's the rate of change of the radius, or the derivative of the radius. So in this case, it's just 2. We can put the units here, although usually you're just going to leave the units for the end. Notice that if the problem had said that the radius is decreasing, well, then I would have had a negative 2 here. So you have to read the problem carefully. Now, what is the question? How quickly is the area changing? So that's asking you to find dA dt. Because again, it's about a rate of change. And it wants to know dA dt when the radius is 5. Well, the idea here is that since a and r are related by this equation, that if I want dA dt, I want dA dr times dr dt. dA dr is just kind of the natural feeling derivative. It's the derivative of a where r is the variable. And since I have a constant times r squared, well, the derivative of r squared is 2r. So in this case, I'll have 2 pi r for dA dr. And then dr dt, we said, was 2 centimeters per second. So times 2. Well, so as we see, the rate of change of the area actually depends not just on how quickly the radius is changing, but on the current value of the radius itself. And so in this case, since I want the rate of change when r is 5, we'll just plug that in. So 2 pi times 5 times 2, so altogether 20 pi. And the units on that is going to be units of area divided by units of time. And in particular, since the radius was measured in centimeters, this will be units of centimeters squared per second. So that's a typical related rates problem. What you'll see is that related rates problems, they all look really different when you look at them up close, because many such problems start out as word problems. And so the challenge is really to convert the problem into kind of an abstract related rates problem, one where you can just throw away all of the words, but still have all of the information. And when you do that, eventually every related rates problem essentially looks like this. So we'll look at some examples. First, an abstract example, and then a couple of word problems to help you see how to work on related rates problems.